Good afternoon, and I welcome you all to this lecture session of the course Laws of Thermodynamics. Now today I will give you a brief introduction to the third law of thermodynamics. Third law of thermodynamics. In fact, the people working in the field of engineering science know very little about third law and its concept, not much. This is because of its limited use in engineering calculations, but definitely it has a contribution in the calculations of engineering science. I will tell you, and then I will explain as much as I can the concept of third law. So far we have defined entropy from the classical thermodynamics point of view through the heat transfer in a reversible process, and we have seen that this definition has come out at its very first step in terms of the difference of entropy or change of entropy in a process from one state to other state. That delta S is integral of del Q reversible by T. That means if a system executes a process at internally reversible condition, then what is the amount of integral del Q by T is del S. So always we define the entropy in terms of its changes. Okay, and in all engineering calculation the changes are required, but sometimes we require the absolute entropy. But even if we don't require absolute entropy, the changes are known, but if you have to ascribe the value of entropy, it is not exactly the absolute entropy from an absolute datum, but you have to fix a common datum. The third law of thermodynamics tells that common datum where the entropy can be taken as 0, or entropy is actually 0 of a substance. So these statements, to understand, we have to understand little bit of microscopic point of view of thermodynamics or microscopic thermodynamics. Though this is totally beyond your scope of calculations or usefulness of thermodynamics in your at your level, but we can discuss this little bit. Now we know from the kinetic theory of matter that molecules moves at random in different directions and they collide with each other in any matter. Now this randomness or disorderedness of the molecule is actually the measure of entropy. The randomness or disorderedness are meant by the variation of velocities over a higher spectrum, large variations, and they are changed very fast. They are changed. That means more randomness or more disorderedness means the velocity, its magnitude and its direction changes very fast and over a large spectrum. If it happens in any matter, we will tell that disorderedness or randomness is more. So more is the disorderedness, more is the randomness, more is the entropy. Now what happens because of this disorderedness or randomness of the molecular motions, it becomes difficult to predict a particular molecular configuration for a given macroscopic state. That means with this randomness, the predictability of molecular configurations or the molecular positions, or we can tell the molecular state, sometimes it is told as microscopic state. To define a particular microscopic state for a given macroscopic state, it becomes very difficult. It becomes much less predictable, which means that with this randomness and disorderedness of the molecules, a given macroscopic state at thermodynamic equilibrium, which so far we have discussed, may have a number of possible molecular configurations or microscopic states. And more is the disorder, more is the randomness, more is this number of microscopic states. That means the uncertainty of defining the microscopic state increases, becomes less predictable. Okay, and that way entropy increases. So it is not surprising at this stage to understand that a substance in solid phase will be having less entropy than that in gas phase, because of the fact that in solid phase the randomness is much less compared to that in gas phase, and the molecules in solid phase usually oscillates continuously about an equilibrium position. So, therefore, absolute entropy in solid phase is less than that of gas phase, where randomness is much more, and they collide frequently, the molecules collide frequently and the randomness is much more. In statistical thermodynamics, this is explained, or this is written in a mathematical form through a parameter known as thermodynamic probability. In its very simple concept, very preliminary and simple concept, the thermodynamic probability is the number of probable microscopic states with respect to a given macroscopic states, and it depends upon the state variables at that macroscopic state. For an example, I am telling you, we have considered an isolated system. You know what is isolated system? Which does not interact with the surrounding. A isolated system is at equilibrium, it does not interact with the surrounding, its properties remain invariant with time and uniform throughout the mass of the system, but it may have a very high absolute entropy because the randomness of the or disorderedness of the molecules. So, therefore, you see microscopic state is different from that of the macroscopic state, in which way that here for a given macroscopic equilibrium state of an isolated system, we have a large number of probable microscopic states or molecular configuration. So, this is expressed in terms of thermodynamic probability in statistical thermodynamics, that probability indicates the number of possible microstates for a given macrostate of a system, and the absolute entropy S in that case is expressed by a very well known equation K ln P, where P is the thermodynamic probability and K is the Boltzmann constant, and this equation is known as Boltzmann equation. This equation is known as Boltzmann equation, and K is Boltzmann constant. Boltzmann constant whose value is 1.3806 into 10 to the power minus 23 joule per K, which is the unit of entropy. So, this is the absolute entropy in statistical thermodynamics expressed by the well known Boltzmann equation in terms of thermodynamic probability. That means, the possible or probable microstates for a given microstates, and where this probability is more means we can have more microstates, more number of microstates for a given macrostates where the absolute entropy is more. So, therefore, absolute entropy depends upon the number of probable microscopic states, which in turn depends upon the molecular disorderedness or randomness. More is the disorderedness, more is the randomness, more is the probability of the microstates. Okay, number of microstates. Now, with this equation, we can understand that how the absolute entropy is expressed. Now, you consider a solid where the randomness is much less, because the molecules continuously oscillate about a equilibrium position, and this randomness, where the less randomness, that means uncertainty is less, also decreases or fades out as the temperature increases. So, this randomness or this uncertainty, even for solid which is much less, also fades out or decreases with the decrease in the temperature, absolute temperature, any temperature, decrease in the temperature. Okay. And when it approaches towards absolute zero, it becomes, the uncertainty becomes minimum. And in this respect, I can tell that we assume that when absolute zero is approached, all molecular motion ceases out. All molecular motions cease out, that means are stopped, there is no molecular motion, and this is sometimes called as ultimate molecular order. That means the order of the molecule reaches its maximum value, and uncertainty is 0 and certainty is 100%. That means molecular configuration is fixed. But if you proceed towards absolute zero for a solid substance, the uncertainty is reduced. The molecular randomness or disorderness is reduced and this substance approaches an absolute zero entropy. And this is more so for a crystalline solid. This is because for other solids, non-crystalline solids, still there are few certain uncertainties, even if the temperature, absolute temperatures approaches zero. So, it is for a crystalline solid substances where when the absolute temperatures approaches zero, we can tell the randomness approaches zero. That means uncertainty approaches zero and molecular order reaches its maximum. So, these concepts were derived from experiments from chemical reactions, data from chemical reactions at very low temperature, data from heat capacities of substances at very low temperature. By collecting the data and through deductions, it has been established. And this law actually was formulated by two scientists, Nernst and Simon, and known as Nernst-Simon statement, which states like that the absolute entropy of a crystalline substance approaches zero as the absolute temperature approaches zero. This is known as Nernst-Simon statement. I will show it afterwards, the statement. Now, with this Nernst-Simon statement, we can have some idea about the absolute entropy. How it is useful in engineering calculations, that to have a common base so that we can ascribe the entropy values at different states from its changes calculated by our well known formula in classical thermodynamics through reversible heat transfer. We can ascribe if we know this base, and that common base, and that is very important, I am telling, in chemical reactions, which has not been taught in this course, that if you read the thermodynamics of reactive systems, then you will see it is very important to have a common base for calculations of entropy at different states of the substances known as reactants or products in a chemical reaction, and that base is that zero absolute temperature base where the entropy, absolute entropy is zero. This is of very practical use for in engineering calculations. Now, this is one approach of defining the third law. There is another approach of defining the third law. This comes from the attainability of absolute zero. In fact, I have told that absolute zero is approach, but exactly we cannot have absolute zero, we cannot attain absolute zero in practice. This has been found. You know that there are, probably you know this has not been also taught, that there are various ways of cooling. So, if you cool a system, how much cooling you can do, or to what temperature you can go? You can never go to absolute zero. In this respect, I will tell you in brief what are the methods. There is a method known as Joule-Kelvin effect, the method which uses the Joule-Kelvin effect. Joule-Kelvin effect is like this: if a gas is coming at a high pressure and temperature, is allowed to pass through a small restrictions or constriction where there is a pressure drop because of the mechanical friction, then it is found the temperature of the gas is decreased if we isolate the entire constricted system, decreased, provided the initial temperature is below certain temperature known as inversion temperature. I am not going into that details. That is known as Joule-Kelvin effect. And if you think from the steady flow energy equation, that the first law of thermodynamics applied to a control volume, and if the constricted system is totally insulated, then the enthalpy at the inlet will be equal to the enthalpy at the outlet if you consider the kinetic energy and potential energy changes are negligible. That means, in this case the enthalpy at the inlet and outlet remains same, but this is highly an irreversible process where the pressure is reduced and the temperature is reduced provided the initial temperature is less than the inversion temperature. Most of the gases are cooled by utilizing this effect where initial temperature is usually lower than the inversion temperature to realize this cooling effect. Otherwise, the gas has to be pre-cooled to a temperature below the inversion point temperature of that gas. Okay. Now, this process is known as throttling process, and by throttling a gas like this we can produce a low temperature, and this is utilized for liquefaction of air, okay, and we can produce liquefaction of any gas, and by Joule Kelvin effect we can produce helium at 5 Kelvin today. Now again there is another process to go for a further cooling to reduce the temperature, which is the adiabatic vaporization. That means if you have an helium at 5 K, if you make an adiabatic vaporization, that means entire system is insulated, there is no heat transfer with the surrounding, and because of the vaporization the cooling effect takes place. Okay. So this is another way by go for further cooling. Another way of cooling a system is by magnetocaloric effect. This effect is known not much. This is that on a paramagnetic substance, by decreasing the adiabatically the magnetic field, we can go on changing the temperature to a very low value. But in all these processes of cooling, it is observed, and it comes from the common sense also, that as you cool, the cooling becomes more tough. For example, when you compress a gas, the compression becomes more tough as the pressure is increased. As you compress, the next compression becomes tough. Similarly, as the cooling proceeds, if you cool, the next cooling is more tough. So this way, if you have a finite number of processes, you can never achieve to absolute zero. Cooling becomes gradually difficult, so that you can never achieve 0 K, and this has been established from several experiments. So therefore, this statement that the absolute 0 can never be achieved in any finite number of processes executed by any system is also another way of defining the third law of thermodynamics. So therefore, we have two ways: one by defining the absolute entropy, its base, where the absolute entropy is 0, we use it as a base for entropy to ascribe the entropy at different states for our calculation, engineering calculation. Similarly, the third law is also explained in terms of unattainability phenomena, that absolute 0 can never be approached. So I now show you the two statements of thermodynamics. Nernst-Simon statement. This statement is the entropy of a pure crystalline substance approaches 0 as absolute temperature approaches 0. That, as I have explained. And another is the unattainability statement, which is that statement by no, this is the statement of unattainability phenomena. What is that? That is, by no finite series of processes is the absolute 0 attainable. So therefore, these are the two statements of thermodynamics third law. We do not have to put much in it, much effort in it, only an overall understanding and a brief introduction of third law. For the completeness of the course, it is required, so you must know there are 4 laws of thermodynamics. One is Zeroth law, which defines the concept of temperature, which defines the temperature, gives the concept of temperature. Another is the first law, which is nothing but typically the law of conservation of energy. Okay. The second law, which is the law that puts a directional constant, which imposes a directional constant or unidirectional characteristics of a process occurring in nature, which has been dealt elaborately how this constant or unidirectional characteristics is imposed on any natural process. And last one is the thermodynamics third law, which defines the absolute entropy at absolute 0 state, which is again not attainable, through two statements. One is Nernst-Simon statement, which defines that absolute entropy, which tells that the absolute entropy of a crystalline substance approaches 0 when the absolute temperature approaches 0, and absolute temperature cannot be attained in any finite series of processes, which is unattainability statement. Okay, by this I conclude. Thank you all.